Howdy folks, so in this video I want to start off first with a review of adding rational expressions, but our eventual goal is to get to the point where we are simplifying complex rational expressions. And we'll see exactly what we mean by that in a little bit. Okay, so the first thing I'd like to do is for a review, I'd like to add together these two fractions, and I know that you might be able to add these together very quickly. You might be able to immediately see the least common denominator. What I'd like to do is, just to get us ready for what comes, let's practice breaking this down into a product of prime factors. So this would be 2 squared times 3. And if I were to rewrite this as a product of prime factors, the value 18, that would be 3 squared times 2. And so here we can identify that the least common denominator would be 2 squared times a 3, because I need all the factors of this fraction, and then I need also all of the factors in this fraction. Well, this fraction right here has a 2, but I've already got, in fact, 2 squared, so I've already got that covered. And it needs a 3 squared, but I've already got 1 3, and so we just need one more factor of 3. So our LCD would be 36 here. And I know that you might have been able to identify 36 as the least common denominator across these two numbers without writing this out, but this is the part right here that carries over to when we add rational expressions this way. So I just wanted to review that. So now that we've got that, we've got, again, 5 twelfths plus, let me leave a little bit of space there, plus 7 eighteenths. We're going to now multiply both of these expressions by the LCD, or by the missing factors from the LCD. So this first term, 5 twelfths, it has the factors 2 squared times 3, and so it's missing 1 power of 3. So I'm going to go ahead and multiply this by 3 over 3. This second term, whose prime factors are 3 squared and 9, they are missing a 2 from the LCD, so I'm going to multiply this one by 2 over 2. So continuing, we end up with 15 36ths plus 14 36ths, which gives us a total of 29 36ths. And then I check to see whether this itself, this new fraction, reduces, and in this case it does not. So this is good practice, folks. You need to get good at working with these fractions. So I'll let you go ahead and try this one. So please pause the video and answer this question, and I've included at least an answer for you. So pause the video and answer this question. Okay, so hopefully you've done that. Now I'd like to extend this. So this is actually what our goal is to add together these rational expressions, and the work looks the same. So we want to add together this fraction to this fraction, and just as we did before, it's going to be helpful to identify the least common denominator. Well, in our case, the least common denominator here is, let me make that a colon. The least common denominator is x plus 2 times x minus 3. And so just as I did before, I'm going to rewrite these two fractions, saving a little bit of space. And I'm going to multiply this first fraction right here by any factors missing from the least common denominator in its denominator. So this has the factor x plus 2. We've got an x plus 2. But we also need the factor x minus 3, so I'm going to multiply this by x minus 3 over x minus 3. Likewise, this second term, its denominator has only the factor x minus 3, and it's missing the factor x plus 2 from the LCD. So we go ahead and multiply by that factor. Cleaning everything up, we end up with 2x minus 6 over the x plus 2 times x minus 3. And although I could FOIL this out, generally we leave it in factored form unless we're instructed otherwise, or unless we've got a good reason to expand it. We'll leave it in factored form. And then for the second term, careful, we've got a quadratic here, so this would be x squared plus 2x plus 5x, so for a total of 7x, and then plus 10 for that constant term all over my LCD. So now all we need to do is combine together like terms as we add together these fractions. So we're adding together the two numerators. Remember, we don't add the denominators. We just, how do you add fractions? You add their numerators once you've got a common denominator. And so we get x squared plus 9x plus 4 all over x plus 2 times x minus 3. Always I check. I notice that the numerator does not factor. That's great. If the numerator factored, I would want to factor it to see if this contains any common factors that I could potentially divide out. But in this case, I do not. So now I'd like you to, again, pause the video and work this problem here. There is a hyperlinked solution for you. So pause the video, and I'll see you in a moment. Okay, so now I want to move on to the new topic, and we'll get started here. We introduced the idea of what's called a complex fraction. So this is our term, complex fraction. Okay. And in algebra, we're going to let that refer to a fraction whose numerator or denominator, or potentially both, contain a fraction. Okay. So for example, this is an example of a complex fraction. You can see here is this large fraction bar, but sitting inside the numerator, I have a term that has a fraction, and sitting inside the denominator, I have terms that each contain fractions. So likewise, we would call this a complex fraction, as with this, and as with this. Another way to think about that is we have nested fractions. Okay. This is my own choice of vocabulary. Some people use it as well. I'm going to use the term major fraction and minor fraction to refer to the different parts of the complex fraction. Okay. So for example, I would refer to this fraction bar as the fraction bar for the major fraction. And I would refer to, for example, 1/2 as a minor fraction in this expression. There would be other minor fractions, such as 2/3 and 1/4. I'm going to refer to all of these as minor fractions nested inside of the larger fraction. The larger fraction's numerator, for example, is this entire expression. So the larger fraction's numerator, and I should say the major fraction's numerator, because that's the word I'm going to use. The major fraction's numerator is 1 plus 1/2. So we've got the idea of major and minor fractions. Okay. And you can see I went ahead and explained some of that here. This is important because oftentimes, most of the time, or sometimes with complex fractions, it's easy to identify the major and minor fractions. Other times it's not clear, and it's the author's job, or your job as somebody writing out some mathematics, to make sure your reader is clear what the major or minor fraction is. So in this case, I don't think there's any need for clarification. We can spot that the major fraction bar is this bar right here, and we have the major fractions numerator, the major fractions denominator, and we see what all the major and minor fractions are. Here, it's less clear because we have several bars. So to help my reader see what the major fraction bar is, you can see I made this bar longer. That's one way to do it. Another way to do it is to make the bar, when you draw it, thicker. So I want to point out that although these two fractions contain the same sine over cosine over secant over tangent, in both cases, we have these fractions nested differently. So here the major numerator is sine, whereas here the major numerator is sine of x over cotangent of x. And here we have this nested fraction. In fact, this is nested 3 deep. We've got this fraction inside of this fraction inside of this larger fraction, and we try to make it clear to our reader with either the thickness or the length of the bar. By the way, sometimes you'll see me write something like this to denote the major fraction bar when I'm drawing it, when I don't have the ability to use typeface. You might see me write something like this, and I draw a double bar to indicate that major fraction bar. Okay, folks, that gets some of the vocabulary out of the way, and in the next video we will start learning to actually simplify these complex fractions. So I'll join you there in a moment. Thank you.